I'd been a PhD student in ISA long back, it seems. That time, the culture of theory group, I don't know whether it's still there. It was disordered. In the sense, it was hard to define who someone's thesis supervisor was till the time he started writing. So, Chandan, I was never formally associated with, but we had a lot of discussions, and the discussions were not really limited to the faculty members. Much of it, what I learned were in TMSC and Ratna, and many of my juniors, seniors, contemporaries. Thank you, HRK and Chandan. HRK had been helpful not only in academics, but in other ways also, and it's not that difficult to find good scientists, but to find good human being, I'd been lucky. And the association keeps on going. That is, when I meet someone, and the first thing in academic circle, they ask, what did you do PhD? Theory group, ISA. I get some respect, and it lasts for all of 10 seconds till they ask me the next question. What are you doing now? And for last 10 years or so, I'm trying to understand how plastic bags are made. It's interesting, but somehow people don't seem to appreciate it that much. Let's see. I'm not going to take all the blame of what's missing in the models, and I'm sure it's not right. But if someone can sell plastic bags and get multi-million pounds grant, that's Tom McLeish. He has this irritating habit of doing multi-step algebra on piece of paper. Each of step are individually wrong. The final result is correct with the numerical factor. Daniel Reed, I first joined with Daniel and Tom, and Daniel I have a long association with. I was his first postdoc, so he was not used to, and we meet quite often. I end up giving him home tasks. And these are the real people who does the experiments from different universities and companies. I have a plan of the talk. I'll try to give you a pictorial flavor of what these molecules that makes plastic bags. I'll come to some virtual molecules in an imaginary flow because no one seemed to allow me to actual lab. I'll take a deviation to gelation in some copolymers, and finally some future work. This is how plastic bags are made. Still, most of the stuff are made from petroleum. It's synthesized into long molecules. They are ground up. There's it's molten. Then air flows in to make it like a balloon, and it's pulled in. Then another machine chops them off to make the plastic bags. And the chopping off is with a hot wire, so it seals one side. You have the plastic bag. Now, in this part, the plastic is going through a strong shear, and it's beneficial to have low viscosity because then you can make lots of plastic bags at the same time within a fixed time window. And while film blowing, there is a planar extension, and you want the viscosity to become higher, otherwise the whole thing falls apart. And it's probably circular. The bags are normally made of plastic because plastics have this kind of properties that they shear thin and extension harden. The idea is how to understand it. And of course, the companies pays money because hopefully once we understand it, we can make better use of, make better molecules, improve instrumentation. Let's go back to basics. That these are two polymers, polystyrene You take a styrene, and typically all of them have a double bond, the monomers, and some Pacman-like catalyst again breaks this double bond and joins them together. With ethylene, you get polyethylene. You can get interesting things if you have different kind of monomer together, but mostly I'll be concentrating on boarding polymers. Locally, they're difficult because this huge benzene ring doesn't look at all like a methyl group. But once you have just 7 monomer of polystyrene or 5.5 monomer of polyethylene, you get to a random walk-like behavior that once this blob doesn't care about what's on left side or right side. The statistics of the conformation is described by just a random walk. It's dominated by entropy. We'll forget energy altogether. It defines what's called Kuhn length, B, and the energy scale is skating. Now, we are not this Kuhn length regime, but really long polymers, probably 10 to the power 5 monomer. Now, long time and length scale, the details, chemical details are not important except for solid state properties probably. So we can work with bit spring model. This is a typical snapshot from internet. And this is an interesting thing that you take the similar looking polymer conformation, remove the periodic boundary condition, and then run it. Run it for some time. And the different polymers have different color just because you can make out. You can note that the dynamics is not isotropic. The yellow polymer remains in a kind of, it forms kind of tube. That's to do with that two long chains, they can move around, wiggle around, but once they hit perpendicular to each other, they have to drag the other polymer with it. So there is a strong topological constraint in the perpendicular direction, while along the chain axis, it's free to wiggle around. Even though this computer simulation is the easiest way to understand it, long back, Digens and Edwards came out with this idea that polymer looks like that it's confined in a tube. There is a length scale associated with the tube diameter or persistent length of the tube, which itself is doing a random walk. And there is a time scale at which the chain becomes aware of the tube. So when the simulation was first, there was no tube. Only about this entanglement time tau, it feels that there is a tube. It can't move any further. Just some number, there was about 10 monomers forming a Kuhn bit, similar order Kuhn bits forming one entanglement. Sorry. What we are interested in understanding what happens to these materials. If we put in a strain, for theorists, it's easiest that we take a block and mentally put in a shear, instantaneous shear, and assume that everything down to the tube length scale is affine. So in this cartoon, this bit will get compressed, this bit will get extended, these two tube segments. And that means the chains, which originally had random walk conformation, is no longer random walk, but it's been distorted. So there is a stress associated with the conformation, not having the random walk conformation. And it can revert back to equilibrium conformation by going out of the tube. It can relax part of the stress by going perpendicular to the tube axis, but most of the stress it can only relax by somehow going out of the tube. And the way it does is the way you move a heavy carpet, that you form a kink, that then you kick the kink out of the way. You can easily see what the time scale should be. Length to diffuse is the length of the tube. The friction would be number of monomer, which is again proportional to tube diameter, tube length. And so the longest time scale grows as cube of the length of the polymer. All these Z, capital Z, are length of the polymer in units of tube diameter. So it gives what's the length of a tube. Experimentally, things are slightly different. That's the longest time scale grows as 3.4 power instead of 3. And that's to do with that you don't really need to form a kink and move it all the way. That then you need the friction from all the monomers. Quite a bit of stress you can decay by just having the end monomer doing a random walk. It can't do too far away because then there will be an entropic potential to climb. But you can get rid of about square root of Z distance through this arm fluctuation. And that's about all there is for monodisperse linear polymer. When you go to something more complicated, then you need to worry a bit more that the tube is not there. It's the other chains, they are also moving around. So let's imagine that there is a chain which I put it on this plane, and there are other chains in the perpendicular direction. As time goes on, some of these constraints will go away because there was this constraint, another chain that has moved out of the way. Suddenly, the polymer can access quite a large jump. And in tube picture, that as if the potential of the tube is becoming softer, or the diameter is growing with time. Experimentally, one finds that you can mimic this experimentally in a controlled fashion by having some oligomers, short chains, and change the density of short chains. So you know what the tube diameter should be. And tube diameter depends as a power law of amount of material that has relaxed or amount of material that are oligomers. And the stress decay now is some modulus, amount of surviving tubes, and amount of surviving density of entanglements, which is basically the tube diameter inverse with a square root. Now, let's think about a branched polymer, a star polymer. Here, reptation is not allowed because if this branch point wants to move up, then it needs to drag two chains in the same tube environment, which is costly. Instead, it's a Kramer's problem that there is a potential hill it needs to climb, and this is the first passage time scale. And out here, because it's huge, the dilution, because part of the chain have already relaxed, changes the potential drastically. It goes in the exponential. Out here, if you don't consider constant release, then things are nonsense. Let's consider a star polymer, but one of the arm is much shorter than the other two. the short term does first passage problem. At some time scale, it has relaxed. Tube diameter has widened because some things have relaxed. Beyond that time scale, it's like a reptation with some extra friction. H-polymer is similar, that there are branch points on both ends of the backbone. Once the branch points have relaxed, the whole object looks like a linear polymer which can reptate along with the extra friction associated with the branch points. Now, we have almost all the ingredients for understanding LDPE, not quite. There are problems. That a typical plastic bag has molecules that vary between 100 to 1,000,000 carbon per molecule in the same bag. And number of branch points can be anywhere between 0 and a few hundred. We do not know what the molecular structures are. And even if someone told, I already showed that it's a hodgepodge of different models. They're roughly valid in different time scales. So we need something really, it's asking for if, then, else, if, else, and go on. So there have been attempts to write down an analytical expression for the stress decay, for star linear blend, for comb linear blend. Each of them takes typically a couple of PhDs and have an expression that takes several pages. Ron Larson came out with this idea that this problem is begging for a differential approach and let the computer do the hard work. Take a mixture of these molecules in computer, assume that there is a step strain, figure out what can relax in a small time interval, update tube diameter accounting for the relaxed portion, and loop over it. It's a simple idea. Larson ignored multiple levels of branching, and the problem, you really need a computer because in reality there are a lot of different kind of molecules. And each one affects the relaxation of everyone else because they collectively decides what's the tube diameter is, which decides what the dynamics is. And if there is a good idea, you always want to steal it and rebrand it. So what we need is have some way to generate an ensemble of representative molecules on computer. You don't want to write down one linear, one comb molecule which looks like 3 arms, another with 4 arms. It's tiring. So another thing is incorporate branch on branch structure. Figure out some way to predict stress in nonlinear flow. Polymer processing almost always involve highly nonlinear flow. We'll come there. Oh, by the way, this, when you rebrand it, give it a name which is easier to say. It's called Bob, and it's on source. Let's consider this problem that there is a long segment which is attached to something else on that side, I don't care. There were some side arms which have relaxed. What's the dynamics of the endpoint should be? It's a multidimensional Cramer's problem, hard to solve. One way to cast it back to one-dimensional problem by demanding that the spring constant should be same as the different segments joined together, and the displacement should be same such that if all the friction were at the end or distributed along the branch points, the dissipations are equivalent. Doing the algebra gives rise to this picture that in our algorithm, small z of t is how much material have relaxed from the ends. Once it gets to a branch point, then before the branch point, it's a star-like arm always, that there is a pivot point about which the end monomer is trying to climb. Once this side arm has relaxed, then it takes a while for the information that there is another branch point there to transfer to the end monomer. Instead, we have a pivot point, which is Z tilde, that it itself gets a dynamics of its own. So every time, however complicated the molecule looks, we recast it as a 1D problem as we follow the time evolution. For nonlinear flow, I need to introduce yet another molecule. It's called pom-pom molecule. There is a backbone and side arms. What flow does is that it aligns and pulls things. Let's consider what happens if I have a uniaxial extensional flow. It's trying to pull the tube this way. Because of the branch points, you will keep extending unless the branch point can retract. So there are two time scales. One is stretch relaxation time. That's the time scale of the side arms. Another is orientation relaxation time. That's the reptation type of the backbone. Now, if we know how pom-pom molecule behave like in nonlinear flow, we can always pretend that any molecule, bits of the molecule looks like a pom-pom molecule. We need to assign orientational relaxation time to each bit of a molecule, stretch relaxation time, and number of side arms. That's basically telling that what's the maximum stretch that it can support in flow. We already know that orientational relaxation time, when we are thinking about this virtual step strain, we have the stretch relaxation time, that's this Z tilde variable. We need to invert both of them. We don't know the number of side arms because typically molecules are not pom-pom. So let's take an arbitrary molecule. LDPE molecules often look like this, with the added complication that there are small, short side arms. We want to convert this red bit of the molecule to a pom-pom. When you are stretching this molecule in a flow, then just by looking at the molecule, we know that the first failure would be from the right hand, because there are less number of branches. So that's the maximum. When it reaches the maximum stretch, the right hand first go inside, concentrate on the right side. Each of the chain end, because it's confined in a tube, it has more degrees of freedom to choose from at the end than inside, translates to a tension at the chain ends. It's just count the number of chain ends and get that it can hold 9 kT over A with a multiply by 3 tension. Something else that if the flow is slow, if I pull it really, really gently, then some of the side arms won't contribute to this tension, because they would have gone back to the origin again and again. So this branch point is not really branch point in terms of holding a stretch. That means we have to repeat this calculation once we know what's the current extensional rate is. This is the idea. Somehow you generate an number of molecules. It can be large, depending on what the molecular distributions are in a material. After a step strain, you follow how things are getting out of the tube, how tube itself is evolving. And each time step, you pretend that they are Maxwell modes. They are giving a linear rheology prediction. Each of the Maxwell mode, you associated also the stretch and orientation relaxation time and number of side arms. That gives a set of pom-pom modes. They are giving the nonlinear flow prediction. That's the framework. So far, I talked about the relaxation modulus G of T in linear regime. Unfortunately, the interesting bit is over a large number of decades, you don't get a transducer which can measure at the same time gigapascal to 0.21 Pascal. Instead, experimentally, you do FFT. Take a Conan plate rheometer and do a small oscillatory shear. Do it at different frequencies, join the results together, and get G prime, the viscous and elastic moduli. The data points are experiments on some good quality linear polymers. Lines are from the code. For nonlinear flow, the simplest experiments are startup shear. The same rheometer, instead of doing oscillatory small amplitude movement, you do it continuously, keep on rotating. For different rates, these are the shear viscosity, that is stress over strain, and the predictions. For uniaxial extension, it's a difficult experiment. You take a bit of material and pull it exponentially fast with time, so that rate is the same. And these are the extensional viscosity for this material is actually LDPE. But before explaining how I got this data, we'll take a detour. We have worked quite a bit on modern polymers. This Cayley tree, and I like this data because it went through a cycle. The original idea was that design a material third generation Cayley tree. This is the second one. That would have length scale such that there are well-defined features in the viscous moduli, and it's within the experimental window. It took about 5 years to actually synthesize the molecule. And this normal GPC, this what's called TGIC, they change the temperature and solvent to get different portions together. There were still about 12% material which had one of the teeth missing. You get only in gram quantity these samples. And I'm coming to this idea that it's difficult to fit the model compounds because they're so pure that it's hard to figure out what's there. There are always impurities, but they're just taking it below the limit of analytical instruments, but unfortunately not for rheology. So the dirty materials are best. These are some data on star polymer. Give a sticky block at the end of the star polymer. Depending on the sticky part, you get first 2 star joined to make a H-polymer, then a comb-like molecule. The 4th generation can have 2 different structures. The nice thing about it is that GPC, you can see different peaks for the different molecules. You don't really know for the larger molecules, but assuming that there is a single probability you can figure out from just the first few peaks what are the other molecules should have been in the soup. And here's the rheology. Again, the prediction, I need to assume a probability. And they had a set of GPC estimates. They're quite in agreement. Except the original star polymer, also my calculation shows that it has a bit things stuck. That can happen because there is always some trace oxygen that can link the parent stars. Another gelation ensemble polymers that you take oligomers with sticky tapes which have either 2 ends or 3 ends. So you end up with a random length linear segment followed by a branch point. Depending on the amount of this red and purple stickers, you can it's arbitrary. You can reach gelation. I can fit the structural data to find rate constants and predict what's the viscosity should be, how it diverges with the molar mass. Now I come back to polyethylene. Last 10 minutes. This high density polyethylene. You have a ventilation catalyst which really look like a Pac-Man with the metal at the front, which eats ethylene at a certain rate. Sometimes it falls off with a terminal double bond. Another Pac-Man, when it's growing a chain, it's looking for double bond really. So it can find it ethylene or in this long chain with terminal double bond, which is called macromolecules. It forms branches. This is an extremely well-defined system, but the catalysts are costly. So plastic bags are not made from this material. These are a series of high-density polyethylene and with increasing branch point density. Because the number of chains with terminal monomer is not rare, by definition, there is much more monomer than chains. So one way to increase the branching is by giving a molecule which has a double bond at both ends. These dienes form pendant double bonds. Another molecule can join in those double bonds. These are some data on propylene-diene copolymer. As diene is increased, it forms a long tail. Eventually, it should go to gelation. These are, so the way I did it is try fitting the molar mass distribution and predict the rheology. Once we predicted the rheology, we can blend any of these two together because we have the molecules in computer. So these are what happens if I mix the molecules in the computer and the experimentalist mix molecules in their pot. They kind of agree, it's satisfying. How to define a gel point? Let's say that there is a gel point DC. There is a reduced distance to gel point. The molar mass develops a power law term, and with a characteristic cutoff, the StatMech community believes that the gel point is where the characteristic molar mass diverges. Polymer community often believes that where the weight average molar mass diverges, that is the second moment, which is wrong. But typically that's what happens, that if we take the diene copolymer, increase the amount of diene, then the molar mass distribution fits with the power law with exponent 2.5, which is classical exponent, and there is a characteristic molar mass which diverges, and MW diverges at a certain critical time. In CSTR, things are quite different. That there is two different power law regimes. The really tail of the tail power law that develops quite late. The exponent is very different from 2.5. The first moment to diverge is the fourth moment. That is, if you measure, you can reach the gel point without having the weight average, number average, or what's called Z average molar mass diverging. This is another representation of the same thing, that you can always fit power law, which gives a critical dyne concentration. If you try doing it with the MW, second moment, you'll find that second moment and third moment critical concentrations don't match. You need to go to fourth moment so that the higher moments give the same critical concentration. The dynamics also is self-similar close to gel point. So viscosity diverges with some exponent. The semi-batch exponent looks like that the exponent is 4.5. It's typical of gelation with entangled segments, long polymers. CSTR, even though the chains, I know that they are entangled, the exponent is more like Rao's regime. And that's to do with this thing, that the inset is what normally experimentalists measure the way it's plotted, that log linear scale, the weight distribution. Now, the lines are for CSTR, and the symbols are for semi-batch reactor at two different distance from the gel point. Unless you go to log-log scale, you don't see difference that these two different epsilon data are different in CSTR. That's because there is an exponential time scale of staying in the reactor, and the really long polymers are only from those long-lived molecules, which has all the side dynes reacted. So the probability is not same like vulcanization, and the classical mean field theory is not working here. I must come back to LDPE, the stuff plastic bags are made of. It's a free radical polymerization at high pressure. There is initiator which breaks down to free radical. It acts in monomer. Two of these growing chains can terminate by combination or by shifting the radical inside, forming a double bond. The terminal radical can hit a middle of a chain, leading to branching or scission. We tried to fit the molar mass distribution and what's called G factor. If a branch molecule has smaller radius of gyration, this is the radius of gyration of a branch molecule normalized by what the radius of gyration of linear molecule of same molar mass should be. These are 6 different LDPE. These resins are commercial resins. You can buy in tons. And their shear and extensional behavior. It's quite well, it fits the experimental data quite well without having to do much data fitting. But of course, I'm still getting paid, so there are things I don't understand. Recently I worked with this Cayley polymers where they, after you do extension or shear, nonlinear, you stop and still keep on measuring the stress. The stress decay initially follows what tube theory is suggesting. Then somehow it holds it for much, much longer. It's a bit reminiscent on some other experiments. It's a bimodal polyethylene. The shear rate is such that the high molar mass material is stretched. Initially, it follows a Diodoid prediction of how it should relax back. Then, even though it's above the melting temperature, the system somehow finds that there is a crystalline minima. Let's hang around a bit. So energy is still a bit important, and that's what I'm trying to do next. That there is a project with Richard Graham in Nottingham and Tim Cock in Bradford is doing molecular dynamics and kinetic Monte Carlo simulation. Our role is to come out with constitutive model for polydispersed melt and put it in finite volume simulation. And Tim is doing the actual experiments. So the idea, what we are doing is try to get the whole pictures inside model, inside the computer with a series of connected models and come out with better plastic bags. Thank you for your attention.
So the dynamics is only induced externally by the shear and by the extension that you have. Is it possible to put sort of polymerization and depolymerization happening actively in the medium while you look at the rheology?
Yes. So if you take these LDPE molecules, they are huge. So when in a shear, to first approximation, it's a dumbbell with the large friction at both ends. So it's quite often with highly branched molecules, it will fall apart predominantly at the middle. So some of the LDPE data, you need to include this in the synthesis step itself. While synthesizing, if a molecule becomes too large, it breaks down at this center. You get a molar mass distribution that has a shoulder. Yeah, it's possible and can be taken care. It's computer, so you put in one extra if then else.
I have one question. Why are plastic bags in general hard to decay?
Because there are very few animals who have any way to get energy from it. Most of the decay are because there are some organisms are eating it.
But usually they break some polymers to get their energy. This is also just
yes, but somehow there are not many who does it for polyethylene. There are some worms which recently they discovered that they eat plastic. That is the scientists who are studying it. They thought they'll keep it safe in a plastic bag, and next day it has eaten it. So there are, and evolution in work. So in a few hundred years, probably, if we are still there and producing plastic bags, there will be organisms.
You showed that plastic bags are prepared from the petroleum, right?
Yeah.
Raw materials. Why can't you just go back? Is it too costly from plastics to petroleum?
Yeah, plastics to petroleum. Yes, you can go back. It's too costly because the main cost for producing plastic is not really joining the molecules. Rather, taking the petroleum and purifying it so that all the catalysts do not die immediately. There are a fraction of molecules, a fraction of plastic bags go back to making plastics again, not necessarily petroleum. You can make petroleum. Again, the main obstacle is that it can kill all the catalysts. So the producers don't like unless someone like you heavily subsidize it. Petroleum, the maximum would be about 100 carbon. Carbon-carbon single bond is quite strong. The main difficulty is breaking. So let's